Here is a summary of the 4 fundamental property relationships that I derived in the last video. You may be thinking to yourself at this point, well, how does this help? So I'm going to use these fundamental property relationships to determine some other identities that I can use when I'm solving thermodynamic equations. So recall that if I have Gibbs phase rule is equal to 2 and my degrees of freedom is 2, I can express any property that I want as a function of any 2 other properties. So for instance, let's say I said that internal energy U is equal to U as a function of S and V. Remember that I can express the differential change in U. I can say that du is equal to the partial of U with respect to one of the independent variables, sorry, ds at constant V times ds plus the partial of U with respect to V at constant S times dV. These d's should be total derivatives. Inside the parentheses should be partial derivatives. Outside is total derivatives. All right, so compare this expression that I just wrote by just taking the fact that my property is a function of 2 other properties and compare it to the fundamental property relationship. Because du has to be equal to du, I can simply say that this thing must be equal to t, and this partial derivative must be equal to minus p. That's the only 2 ways I can get only ways that I can get the 2 sides of the equation to be equal. So these are helpful identities. So we can say that t is equal to du ds at constant v, and minus p is equal to du dv at constant s. And these are, again, always going to be applicable. I forgot my underbar there. All right, so you could do the same thing with h. So you can say that h is a function of s and p because those are the derivative terms. H is equal to h of s and p. And you can take the total derivative. So dh is equal to partial of h with respect to s at constant p, times dp, times ds, plus dh ds at constant p times, I did the same thing twice. I need dh dp at constant s, and then this one is dp. All right, so comparing it again to the fundamental property relationship, dh ds at constant p is also equal to t, and dh dp at constant s is equal to v underbar. I think this is the identity that we use, or maybe it was another one, but we got it equal to v underbar. So you can continue on and do these for Gibbs free energy and Helmholtz energy as well. And you can always use these relationships. Notice how it's helpful, right? So if I have dh dp at constant s anywhere, remember that h and s are properties that I can't necessarily measure easily. So instead of expressing it like that, I could rather express it as v underbar. That is something that I could measure out in the process plant, and that's what I want to work towards, is expressing everything in terms of p, v, and t, the things that I can measure. So this discussion gets us into another very important part of Thermo 1, which was the Maxwell relations. So I'm going to derive those next. Maxwell's equations. So Maxwell's equation starts by recognizing that another property, useful property from partial differential calculus, says that when you take the second derivative of a function with respect to both independent variables, the order doesn't matter. So in our xy notation, I can say that the second derivative of x taken with respect to y first and then with respect to z is equal to the second derivative of x with z first and then the partial with respect to y. So I'm going to use this in order to take the second derivative of the function to see if I can derive some other useful relationships between these thermodynamic variables. So taken from above, I'm going to take the two properties that I got from the fundamental property relationship for internal energy. So from above, I got that T is equal to the partial of U with respect to S at constant V, and I have P is equal to minus du dV at constant S. So now I'm going to take the second derivative of each one of these terms with respect to the other variable. So in other words, I'm going to say d dV of du ds at constant V. And okay, so hopefully my handwriting isn't that neat. I just took this term, this du ds at constant V, put it inside the brackets, and then took the derivative of that whole term with respect to V at constant S. I'm going to do the reverse for the P term. So I'm going to say that d ds of brackets, parentheses, minus du ds, oops, sorry, du dV du dV at constant S. And this bracket is at constant V. All right, so by this rule of calculus that I said above, that means that these two properties should be equivalent to each other, right? Because I'm taking the second derivative of U with respect to V and S, and the second derivative of U with respect to S and V. Notwithstanding this negative sign, I need to account for that. But importantly, I can substitute in that T I can put in for this whole expression, and P I can put in for this whole expression. So in other words, I could say that dt dV at constant S is equal to minus dP ds at constant V, which you might recognize as one of the Maxwell's relations. So this is a Maxwell equation. This is our first Maxwell equation. And I can go through and do that for the other four fundamental property relationships that I just introduced. So I'm going to write down the fundamental properties that I get from enthalpy, and then I'd like you to pause the video and see if you can derive the Maxwell relation that you can obtain from that equation. So here I've transcribed the relationships that we can obtain from the fundamental property relation for dH. So we said that T was equal to dH ds at constant P, and V was equal to dH dP at constant S. And I keep forgetting these underbars. All right, so this tells us that H is the dependent variable, S and P are the independent variables. So I can take dt with respect to the other variable. So I'm going to take the variable I'm keeping constant, take the derivative of that variable with respect to, keeping the variable that I was taking as the respect to the outside is equal to d ds of V at constant P. All right, so just written a little bit neater. Again, imagine that I'm putting T and V, or equivalently the expressions for them such that they're equivalent. So it's dt dP at constant S is equal to dV ds at constant P. All right, so I'm going to teach you a useful mnemonic now so you don't have to go through with doing this derivation every time. So in my mind, I like to just imagine the variables kind of switching places. So the green goes with the green, the gold goes with the gold. To derive the Maxwell relationship from the fundamental property relationship, I take the variable that doesn't have a D in front. So I just take T and V, and those go on the top of those become the independent variables. And the dependent variables are the ones with the D's in front. And I just flip-flop them while keeping the other one constant. So it's dt dP at constant S, and then plus dV ds at constant P. And using that mnemonic, I can go through and do the other to Maxwell relationships. So I just wanted to write the 4 Maxwell relationships that we derived in this section for you nicely and neatly. Be aware that there are other Maxwell relationships. We may or may not use them. Again, I'm not really sure quite yet, but I would start keeping a page in your notebook of just useful information that you may need for later. And these Maxwell relationships can definitely get filed away on that page.